Start over. Every spring, ranchers face the same challenge, trying to guess how much forage will be available on grasslands that summer for grazing. And GrassCast is an experimental forecasting product that indicates by early May whether individual counties in the northern plains are likely to have more or less vegetation than average. GrassCast translates past weather, current conditions, and seasonal forecasts into a product livestock producers and range managers can more easily use to inform their decisions. GrassCast was funded by USDA ARS, NRCS, and NDMC, and co-developed with Colorado State University, the University of Arizona, and the North Central Climate Science Center. The Northern Plains Climate Hub organized workshops in 6 states last year to solicit input from NRCS and University Extension Rangeland specialists. Dannele will now provide an overview of the GrassCast product, a bit of the science underlying it, and plans for rolling out this summer in the Northern Plains. We ask that you mute your lines. Go ahead and mute everybody except for Dannele. Hold on a sec, Dannele. So I'm going to turn it over to Dannele, and if you could please hold your questions to the end. If you have a burning question, feel free to put in the chat box. But please hold your questions to the end. Dannele will go through her presentation and then address those questions. So here you go, Dannele.
Great, thank you for that introduction, Rachel. As Rachel said, this was a multi-institute and multi-agency effort, a really wonderful example of what we can accomplish when we work together across USDA agencies and also partner with our university research friends. So today I'm really just the messenger for GrassCast, but this brilliant idea really belongs to Bill Parton at Colorado State University and his research assistant Melanie Hartman. They're really the core of this GrassCast team. And then again, lots of partners from ARS and NRCS, several other universities, and then the Climate Hub helping on the outreach side. So let's dive on in. So as Rachel said, you know, every spring ranchers kind of are looking out their windows, waiting and watching, trying to figure out how much grass they might have for the upcoming summer for their cattle to graze. And this is really important because they have to decide how many cattle they're going to keep and graze that summer versus how many they should be sending to the markets. So it's a really important decision that they face and a really difficult one. And, you know, over the years, weather forecasts have definitely gotten better. You know, we understand the science of weather forecasting and seasonal outlooks better. We have faster computers and more data, and this all generates better forecasting skill. The picture I'm showing here, the graph here, is really for 36-hour and 72-hour forecasts. Today, we're really going to be talking about longer-term seasonal forecasts, kind of 1 month to 3 months. But it just illustrates that, you know, over the last 50 years, we really have made a lot of progress in improving the skill of our forecasts. That said, there are still some really important challenges and limitations to our forecasts, specifically for agricultural producers. The first one is that these forecasts really are pretty complex and can be really difficult to understand for the lay public, and even difficult for myself to understand, and I've been working in this world for a while now. And so the cartoon in the bottom of the corner there, you know, saying, I don't know, the forecast for tomorrow is scattered arrows. What the heck does that mean? So that's one challenge. The second challenge, even if someone does understand what the forecast is telling them, it's not automatically obvious what it means for agriculture or how that translates into one of their agricultural decisions that they face. So the second cartoon is showing what would be ideal if we could take a forecast and translate it into the language of agriculture, you know, directly translate it into something that they have to manage, like a locust front map instead of the weather front map. A third challenge is that even if we can get a forecast that's, you know, they understand, that's in agricultural terms, often our forecasts still have a lot of uncertainty underlying them. And, you know, agricultural producers are making decisions that are their livelihood. It's their paycheck. It's their family's way of making a living. And imagine if I asked you to use a weather forecast that was only 60% certain. And I asked you to make a decision based on that information that could determine whether or not your family has an income this year. I think you too would be a little cautious, a little skeptical about using that information until the certainty was higher. So this is a really important issue in agriculture. And then on that note, right, the farther we try to look out into the future, the more uncertain things become. And so we have a tendency in forecasting to hold off and wait and try to wait until our forecasts become more certain. But by that time, often our agricultural producers can look out their window and see what's happening and say, thanks a lot for your forecast. I could tell that by looking out the window. So for really difficult problems when we're trying to provide weather and climate information to producers, today for GrassCast, what we're really trying to do is tackle these first two problems. One, we want to make GrassCast easy to understand, easy to interpret. And second, the whole point of GrassCast is to take seasonal forecast information and directly translate it into the things that a rancher cares about. And that's how much grass is out there on the ground for their cattle to graze. So here we go. That's exactly what we've done here with GrassCast. We take the CPC's seasonal outlook. This is an example from last year, the 3-month outlook for precipitation. This was released last year in late April, and it's telling us what to expect for precipitation in May, June, and July. Those are kind of the critical months for growing grass out on our rangelands here in the Northern Plains. And I often carry this map out with me into the field when I, have a trade show booth at one of the Cattlemen Association meetings, or I'm doing a presentation. And if I just hand this map to a producer, the reaction I get first is, what is this crazy looking map? What is it saying? And second, how do I translate this? How am I going to use this as a rancher? How do I translate this into the decisions that I actually have to make about how many cattle to put out for grazing? And so GrassCast attempts to translate this. And so instead of just presenting a map of the seasonal outlook, we try to translate that and present a map instead of how much grass we think might be available for them in the upcoming grazing season. So in a nutshell, my elevator speech about what is GrassCast. First, GrassCast stands for the Grassland Productivity Forecast. And so tried to find a clever twist on those words, and we came up with GrassCast. Now, if I had this map in my hands and we're trying to explain it quickly to a producer, here's what I would say. I would say, based on the weather we've observed up to this date that we made the map, plus what we think might happen with the weather over the next couple of months, we expect grassland productivity in your county to be this % higher or lower than your county's 30-year average. So that's the punchline. That's how to interpret this map. So some examples. Down in the southeast part of Colorado, you see a dark blue color. Again, this was a map from last year that we produced in mid-May. And at that time, GrassCast was suggesting that in southeast Colorado, in the dark blue, that those counties, to our best information, those counties should have expected more than 30% higher vegetation production, think of as pounds per acre, on their rangelands for the growing season. In contrast, you see a bunch of counties up north in the Dakotas and Montana that are orange. And at that time, again, this was mid to late May, that our maps were telling us that those counties should expect 5 to 29% less grassland productivity, pounds per acre, in their county compared to their 30-year average. So today I want to, GrassCast, I could just give you the map and tell you to trust it. There's a black box behind it that has some pretty complex science inside of it. I don't want it to be just a black box. I want you to have enough of a sense for how we make this product that you can decide whether you trust it or not. So first I want to give you an overview of the process we use to make GrassCast, and then we'll take a little bit of a science deep dive for a few minutes and dig into the black box, and then we'll come back out, take a breath of fresh air, and talk about how well does GrassCast work. So the overview, how do we make GrassCast? Again, we know from rangeland science that in the northern plains, April, May, June, and July are kind of the most important months for precipitation and temperature to influence how much grass will be growing over that entire season, that growing season. And so on the day that we go to make a GrassCast map, we take all of the weather that we've observed up to that date, let's say up to May 14th, and then we've got to fill in the rest of that calendar. Again, May, it's not just April and May that are important to grassland production, but also June and July. And we haven't observed the June and July weather yet, so we have to fill those gaps in with something. And we're going to use CPC's forecast information to fill in what we think the weather will be over the rest of the growing season. So, observed weather plus forecasted weather. We're going to stick this into a model called DAYCENT, and I'll tell you later a little bit more about that. But what this model spits out is evapotranspiration over the entire growing season. So our best estimate of how much water will be moving through the soil and through the plants during the growing season based on what we think the weather is going to be. Why do we care about evapotranspiration, ET? Well, it turns out that how much water is moving through a plant is really closely correlated with how healthy that plant is and how vigorously it's growing, what I'm going to call the greenness of the plant. And for those of you who know about this thing called NDVI, it's how we measure greenness. Just as a little side note, where NDVI is remotely sensed by satellites. It's measuring how much light is reflecting off of plants. And it turns out that healthy plants reflect a different set of light than unhealthy plants or plants that aren't actively growing. And so we can, based on these signals that are bouncing off of these plants, we can actually tell the difference between grass that's growing well and grass that's not growing well. And so I'll just refer to that throughout the presentation as either the greenness or occasionally I'll use that term NDVI. Now that we can see how green and healthy the plants are, it turns out that that's strongly correlated to the thing we really care about, and that's how many pounds of forage or pounds of vegetation is going to grow per acre. And it's that, pounds per acre, that we are using to draw our GrassCast map. So that's the 4-step process involved in making GrassCast. You might ask, boy, that sounds more complicated than it really ought to be. Why can't we just go straight from ET and how much water we think will be moving through the system directly to the thing we care about, pounds per acre? So why are 4 steps needed? And here comes our science deep dive. So everybody take a deep breath. We can do this together. Okay, we can't go directly from ET to pounds per acre because we're missing some data. So here's our 6-state region for the Northern Plains Climate Hub. And for that entire region, for every county, we do have long-term evapotranspiration data. Well, we simulate it using a computer, but we have it and it's good data. And so we have that piece for our entire region. So we've got the first part. Here's the problem. When it comes to pounds per acre, we don't have very much long-term data on this. Even though there are rangeland management folks all over the West taking clippings, going out and clipping their vegetation plots, these data are often short. They're not long enough. They're not consistent enough. And so this is why we need a 4-step process. In our region, we really only have these long-term clippings data sets for about, currently about 4 to 6 different sites in our region. And that's what these little brown stars represent, are the 4 locations in our region whose data we've currently been relying on. But the rest of the region, we don't have good consistent clippings data, and that's what all those red question marks were about. How do we fill in those gaps? We're going to need a middleman to help us fill these gaps in. And that middleman, as it turns out, is this greenness index, this NDVI. We have greenness data for every county in our region. So we've got 3 pieces of information, and at these special sites with the brown stars, we have all 3 data sets, which is marvelous. It's exactly what we need. We have the 2 pieces that we really care about, ET, because that's how weather enters the conversation, and pounds per acre, which is the thing ranchers really care about. But in the rest of our region, that bottom piece is missing, right? We've got ET, but no pounds per acre. And again, we need a middleman to help us fill in those gaps. So here's what we do for GrassCast. We figure out, is there a statistical relationship between these 3 pieces of information? And we look for those relationships at our brown star sites, since we have all 3 at those magical sites. So we test for statistical relationships between these 3 pieces of information at the brown star sites. And I'm going to show you in a minute that those relationships are pretty strong. And because they're that strong, we can then use those relationships to help fill in the gaps everywhere else in our region for every other county. And so we'll use those statistical relationships to move from weather and ET to this middleman, NDVI, greenness, which we then can use to estimate pounds per acre for every county in the northern Great Plains region. So, again, science deep dive, hang in there with me. I want to, again, kind of convince you at a beginning level that these relationships, A to B, B to C, actually hold up. So let's look at the first question, and that's asking, is ET actually related to pounds per acre, right? The 2 things we care about, the weather, which influences ET, and pounds per acre, are they actually related to each other? Busy slide, nobody panic. What we have here is a table of statistical correlations for a site in northeast Colorado. It's the Central Plains Experimental Range near Nunn, and it's an ARS facility. And what I've got highlighted here in the table, I've circled the number 0.5973. What that number is telling us is that when we look at the data at this site, when we compare evapotranspiration across the whole season, and that's what I'm calling in the table, it's called IAET. I just means evapotranspiration summed over several months. When we look at that correlation for evapotranspiration for the months of April through July, about 59 or 60% of the variation in pounds per acre is explained by that. And so ET and pounds per acre are pretty strongly correlated at this site. In other words, if you know one of them, you have a pretty darn good estimate of the other. So this is good news. This means we can use ET as a proxy for pounds per acre. Now, some of you might be looking more closely at this table and you see some higher numbers. There's a 0.644 for transpiration in April through August. Remember that we did this analysis at about a half dozen different sites, and it turns out that the IAET, integrated ET from April to July, is kind of the most robust. It works the best across the most number of sites. And we also like ET because it accounts for other things like not just rain, not just precipitation, but snow, and snow melt, snowpack. It accounts for soil moisture, and these are things that ranchers are constantly telling us matter in their systems. So we like using ET because we have the option of incorporating these other pieces of information that ranchers tell us that for their site are important. If we just used precipitation, we would simply have to tell them, nope, sorry, you know, we don't care about snowpack, or we don't care about soil moisture. And they wouldn't be real happy with that explanation. So we're going to go with ET as the first step in our process for estimating pounds per acre. Okay, so quickly, ET. I told you that we were simulating this data, not actually measuring it. We simulate it using this model called Descent. And all I'm going to say is that you can tell from this picture that Descent is a really complicated model. It's a physical-based process model that has all of the pieces describing how soils interact with plants, interact with the atmosphere and rainfall. So it's a very complex mathematical model. What we know is that Descent has been used all over the world and has been tested and validated and verified. It works really well at describing systems like rangelands. And there's a couple of citations down there at the bottom if you want to dig into the Descent model. But it's a pretty well-known and well-tested model. Just to reassure you a little bit more, the point of this slide is that Descent works really well for modeling ET. Again, in this case, these graphs are for the Seeper site in northern Colorado. The top graph is showing us ET that was observed in Colorado. So the red represents actual observations of ET. And then the blue represents what the Descent model estimates ET is. And you can see that they track really closely together. Not perfectly, but really quite closely. The bottom graph is for soil moisture. For anybody who cares about soil moisture, Descent does a really darn good job of modeling that too. Okay, so we can model ET and do it well. Let's move on to the next step in our black box. The next question is, okay, we have ET. How well does it relate to our middleman, this greenness index, NDVI? This graph looks like a nightmare. Again, nobody panic. Hang there with me. Let me explain this. The first thing I want to point out is that this graph is broken up by state. So you'll see the different labels here: Colorado, Kansas, Montana, Nebraska. Let's focus in on Nebraska that I've got circled. Each of the dots in this piece of the graph represents a different county in Nebraska. Okay, and they're not ordered in any particular, we just gave them numbers and they're ordered here by number, but those numbers are meaningless. Each dot is a county in Nebraska. Now, what do the dots mean? If we look over at the y-axis, I've circled it, it's r square. What this graph is trying to tell us is how strongly correlated, how strongly related is ET and greenness in each of these counties. And you can see if you kind of fuzz your eyes and look for a general line across that graph, that most of the counties are hovering in that 50 to 60% R square. So again, this is saying that if you observe ET, the variability in ET explains about 60%, 50 to 60% of the variability in the greenness data. So again, that's a pretty good positive correlation between them. Now that said, you can also see that in some states, those R squares dip all the way down into 10%, 20%. And what that's telling us is that in some states and some counties, for some reason, there's not a real strong tie between how much water has moved through the soils and through the plants and how healthy they are. And what we found is that as you move further east into wetter and wetter systems, ET is not necessarily the best driver of how healthy and vigorous the plants are growing. But by and large, in our region, again, Colorado, Montana, Nebraska, the Dakotas, there's a pretty decent correlation between ET and greenness. So that's helping us move from point A to point B. Let's do the final step, from B to C. Now this is asking, okay, if we can estimate greenness, does that allow us to estimate the thing we really care about, pounds per acre? Again, this graph is for that same site in northeast Colorado at the Central Plains Experimental Range. You can see in that graph an R-square of 0.649, so again, about 65% of the variability in pounds per acre is explained by or is correlated to greenness. So that's a pretty strong correlation. Again, this is just saying that these two are decent proxies for each other. So yes, we can, if we have greenness, we can estimate pounds per acre. And that was really the crucial piece. Remember all those red question marks across most of our region. This step is going to help us fill in those question marks with estimates of pounds per acre. All right, so we made it. The science deep dive is almost over. Again, down at the bottom of this slide, you see the chain of events that have to happen here. ET to NDVI greenness to pounds per acre. And we've shown that there are strong enough correlations between each of those to allow us to use that chain of evidence. Okay, whew, you survived the science deep dive. Again, big breath, everybody. Come up to the surface. Let's get back to what you guys really care about. How do we make GrassCast in practicality? You know, when May 14th rolls around this spring, what are we going to do to make GrassCast? Well, by now this should make sense to you. Again, we're going to gather the observed weather data up to that date. We're going to fill in the rest of the season with a forecasted weather information. We're going to stick that into the DayCent model, which is going to tell us how much ET is going to occur in each county over the entire growing season. We will run that through our statistical relationship and use it to predict how the greenness index, again, how vigorously the grass is growing or expected to grow. And lastly, we'll translate that to the thing we actually care about, pounds per acre of forage, and that will give us our GrassCast map. So let me break this down to just a couple of, I want to look at number one and just acknowledge where we're getting that weather data from, so that later in the question and answer period, you guys can ask some detailed questions. Okay, so step 1A. We're going to pull the historical or observed weather data for each county, and we're pulling this data from a system called ACIS. ACIS is just this lovely database that allows lots of different monitoring systems and networks and people to share their weather data and make it accessible. So we go into ACIS, and for each county, we identify the latitude and longitude of the county center, because we're only going to provide one forecast per county. It's one of the shortcomings currently of GrassCast. So we identify the location for a county whose historical weather we want, and then we query the database, and it tells us how long was each day, because that influences how much ET, how much evapotranspiration occurs. It gives us the min and max temperature that day, so that we know how extreme the temperature change was, because that influences ET. And then we also get the precipitation data. Again, thanks to our friends at the High Plains Regional Climate Center for maintaining ACIS, and for our friends at National Drought Mitigation Center for helping us develop the coding to automatically pull this weather information. In the future, we would love to be able to account for some additional factors that we know impact ET, things like wind, solar radiation, relative humidity. We know these are important drivers of ET. Unfortunately, there just aren't enough long-term data sets across all of our counties to make use of it and to use it in our modeling. So this is something we would like to do in the future, but until then, we have to rely on our NDVI data, our greenness data, to kind of reflect the influence of these variables. Next step, so we've got our historical data for every county. Now we're going to hone in on the data for the last 30 years, 1986 to 2016. And we're going to use that weather data to simulate evapotranspiration for each county. And again, when I say ET, I really mean the season-long ET. ET in April plus May plus June plus July. And that's what the little I stands for. We're integrating over these multiple months. So we use our historical weather data for these 30 years to estimate what ET was in each county for each of these years. So let's just pick I live in Albany County, Wyoming, and so I would go in and simulate what was the evapotranspiration in 1986 for Albany County. What was it in 87, 88, and so forth. So now I've got my data set for my county, and again, it's 30 years of ET estimates, and I just rank them. I sort them from highest ET to lowest, and that represents kind of the most vigorous and the greatest greenness year to the least vigorous, least green year in the data set. Then I take my ranked data set and I just break it into thirds. And I say, here's the top third, the middle third, and the bottom third. And again, the top kind of most green years, in the middle, and the least green years. And I'm going to use this later, and I'll explain this better in the next slide. But we're going to use these 30 years of observed ET to translate CPC's forecast, their 3-month forecast, into weather data that we actually will feed into DayCent. I know that's confusing, so let's go to the next slide and hopefully I'll make it clearer there. So again, I'm here in Albany County. It's May 14th. I'm getting ready to make my GrassCast map. The very first thing I do is go to the CPC website, and suppose they tell me that for my county, they're expecting above average precipitation for the months of May, June, and July. Well, then I go to my historical data set that I just created, again, this historical ET for my county, and I say, okay, above average, I'm going to go and take the top third of my historical ETs because those are similar to what CPC means when they say above average. So I go into my historical ET data set, I take the top third, and then I use the weather, the May, June, July weather from those years, those top 1/3, that's 10 years. I use that actual weather and feed it into my DayCent model for those months of May, June, and July. So what I'm really doing, right, again, it's this year, it's May 14th of 2018. I want to make my GrassCast map. I go ahead and I enter the observed weather up to that date for my county, what we've actually seen this year. But then I've got to fill in May, June, and July. And I'm going to fill it in with weather that resembles the thing that CPC is forecasting. So I run my DayCent model 10 times for my county, the top third, historical years that also had above average conditions. And DayCent spits out 10 ET estimates for me and for my county. Step 1. Then what do we do? Okay, so again, I'm Albany County. I now have 10 estimates of what the ET might be for me this year. 10 of them because we can't be certain. So we've got 10 different estimates. And we're going to run those estimates through our statistical relationships. We're going to translate those 10 ET estimates into 10 estimates of greenness for my county, and then 10 estimates of my pounds per acre for my county. Well, 10 estimates are a pain in the butt. Nobody wants to look at 10 estimates, right? So the next step is to take my 10 estimates of pounds per acre and average them so that I come up with just one number for my county. In reality, we could present all 10 of those estimates, or we could present a standard deviation, whatever we thought would be helpful for producers. But for simplicity, let's just imagine that we take the average and present that one number, estimated pounds per acre for your county. The final step is simply to turn that pounds per acre estimate into a percent and to translate it and just say, this equates to 80% of your normal vegetation, your county's long-term average vegetation, or, this is 30% more, 30% higher than your county's average pounds per acre. We find that percent, presenting it as a percent difference from what's typical is more more useful than just saying, you're going to have 1,272 pounds per acre this year. Congratulations. Much better to say you're going to have 10% more or 15% less. Phew. That's how we make GrassCast. Here's an example from last spring. On May 8th, we tried, we made this GrassCast map. Now, we all know that the weather changes and our forecasts are not perfect, and our knowledge evolves as time moves on. And so our plan is every 2 weeks, we get an updated observed weather data set. And so we'll update this map every 2 weeks to account for the new observed weather that we've watched. And then every 4 weeks, CPC puts out a new forecast, a new 3-month outlook. And so every 4 weeks, we will run GrassCast again, both with the new observed weather and CPC's new forecast. And so last summer, when we were practicing, here's what a month later, how our GrassCast map changed. And then another month, or I guess that's 2 weeks later, how it changed again. And so you can see our forecast changed pretty dramatically. And you can see that in Montana early on, gosh, things looked pretty positive. And that's because they had a pretty good, snowpack coming out of the spring. And then everybody was caught off guard by the flash drought that hit Montana. And so you can see by mid-June, our forecasts had kind of caught up and went, whoa, wait, we've got a problem here. And by June 30th, our GrassCast map was correctly showing that the problem was getting worse. Okay, so that raises the issue. You can see that, gosh, if we had released the May 8th map, Montana would have been pretty mad at us. So let's talk for a few minutes about how well does GrassCast really perform. And there's two elements to this. How well does it perform across time, from early May through the end of the growing season, July 31st? And how well does it perform across space? We saw that it struggled up in Montana early last year. Are there other places where it does well or struggles? Okay, another scary looking graph. What I want you to focus on here is simply that the dots, as you move from left to right, from early May to mid-June, the dots get clustered together more tightly. And what that's saying is that as we move from early May into June, GrassCast gets better and better at predicting the actual outcome of the growing season. Why is this? It's simple. Again, we know that April, May, June, and July are the important months for grassland growth. Early on May 8th, think about how we're filling in the weather information for those 4 months. We've only observed April. The other 3 months, we have filled that weather information in with a forecast. And if that forecast happens to be wrong, well, then our GrassCast is going to be wrong. Fast forward another month, the end of May. By then, we've observed 2 of the months. We've observed weather in April and May, but are still relying on CPC for our June and July weather. So we're less reliant on the forecast, and therefore it should be getting more accurate. And then by mid-June, we've observed April, May, and most of June. So we can't go wrong. We've got that data is correct. We're still relying on CPC for July, but our map is not that reliant on the forecast anymore. So of course it's going to be more accurate. Here's a different way of looking at how that accuracy evolves through time. Over on the left edge of this graph, if we tried to produce GrassCast at the beginning of April, again, we would be relying entirely on the seasonal forecast. And we all know how hard it is to develop those seasonal forecasts. They're not very accurate because it's such a complex system. And therefore, in April, our GrassCast does a terrible job, frankly, of predicting how much grass might grow over the entire season. It's correct only 10% of the time, or in 10% of the counties, GrassCast identified the correct category. Not good. As we move to the right, we can see that in early May, we're still only at about 20% of the counties being correctly categorized. Still not real good. By mid-May, we're getting up there towards about 50% of our counties. GrassCast is correctly categorizing them, correctly identifying if they're going to have, 10% more or 10% less, 20% more or 20% less. And then by the end of May, we're up there at about 70% accuracy. So if producers can afford to wait that long, by end of May, in 70% of our counties, GrassCast is likely to get it right. And of course, if you wait till the very end of the growing season, we should be able to get almost 100% accuracy, but that's not going to be helpful to anybody. So you can see this trade-off between trying to provide information at the time producers are actually making their decisions or in advance of their decisions. Ranchers would love to have this information by the end of April, early May, because that's when they would like to make their decisions about how many cows they're going to keep or send to market. But that comes at the risk of giving them a forecast that's not accurate and potentially leading them down the wrong path. But if we wait too long, right, of course, as we wait, our accuracy improves, but the usefulness of that information starts to decline. So we're thinking somewhere around mid to late May, we would feel most comfortable revealing this information, but that's still up for discussion. One last one, this question about how well does it perform across space, across different counties. Here are just two examples, Weld County, Colorado versus Lincoln County, Nebraska. Now the data in this map is asking by the end of the season, so the last GrassCast of the season, that late July GrassCast, how well does it do? It now has full information about the weather. How close did it get to reality in predicting pounds per acre? And in Weld County, it's pretty darn good. An R-square of 0.92, so 92% of the variability in the actual pounds per acre is captured by GrassCast. Now in Lincoln County, Nebraska, that same number is only 74. So we're only capturing 74% of the variability there. And again, this is just acknowledging that in wetter portions of our region, those statistical connections between ET, greenness, and pounds per acre aren't as straightforward. They're a bit weaker, and so our GrassCast is not going to perform as well in those regions. We've got a lot of work ahead of us in this aspect, trying to identify which counties GrassCast works best for and which ones are problematic, trying to figure out why they're problematic and see if we can overcome them. We always get asked, how well does GrassCast perform in predicting dry years versus wet years? So here's the year 2002. On the left is actually what happened and how much grass grew in the region. On the right is what GrassCast says on July 31st with full weather information. This is what GrassCast said would grow. So you can see overall we've got the patterns pretty darn, the broad patterns are correct. There's a few counties where we may have been one category off, but pretty darn close. And in fact, 78% of the counties had the correct category. Here's a wet year, 2009. Again, broadly, looking at the colors and the patterns, GrassCast got the patterns right. And in some counties, we may have been one category off. We said there was going to be a little bit more grass than actually turned out. But overall, 76% of the counties were correctly classified. Again, this is on July 31st when GrassCast had all of the observed weather information. And so what this is telling us, if you have good quality weather data and forecasts, GrassCast is quite capable of correctly predicting pounds per acre. The big question becomes, how good are your forecasts? That's really the Achilles heel of GrassCast. One last statement about how well does GrassCast work. Thankfully, we were never completely wrong in our predictions. Never did we suggest it was going to be above normal, and it turned out to be completely opposite, below normal. We're typically just off by one category. So maybe GrassCast says it'll be average, and it turns out to actually be, slightly above average. But we were never wrong in the completely opposite direction. So that's encouraging. Last discussion, and I'm going over time a little bit here. Ranchers want information sooner. They would love to have this in late April, early May. We already know that we can't use the CPC seasonal forecast that early, or we risk being very wrong. So our team is discussing, is there a different way to present this information, get it to them sooner without such a big risk of being wrong? And our idea here is that maybe in the early season, again, let's say May 1st, we've observed the weather for April, put that into our model. And for the months of May, June, July, what if we did some what if scenarios? What if we ran GrassCast saying, okay, what if from this day forward, precipitation was above average? What would the GrassCast map look like? What if instead from this date forward, we just got average precipitation? Then what would GrassCast look like? And lastly, from this day forward, what if we got below average precip? Then what would GrassCast map look like? And here's what this would look like. We would present 3 maps that would give producers a sense for how big the range of possibilities are. Ideally, we'd be able to assign a probability to these maps to show which map our experts are leaning towards. I love that idea. It's a little bit more complicated because each county would need its own set of probabilities, but I think we're on to something here. I'd be interested to discuss it with folks. So to wrap up, our plan is to roll out GrassCast this spring. Again, it'll probably be mid to late May to be cautious this first year out of the gates. Keep an eye out for it. We're going to be developing a basic GrassCast website. A more advanced one will be coming the year after. We'll be reaching out to our NRCS friends in the service centers across all these counties, along with the conservation districts and our friends in Extension. Right, they're our boots on the ground. They're the ones who can get this information to ranchers and help explain it. Watch for it in some of our regional ag newspapers, and then we'll also be doing some invited talks. And I would say if you have any events where you think this information would be useful, let us know, and we'd be happy to consider coming and talking about it. Moving forward with the research, here's our plan. This spring, we're going to continue doing the validation for the Northern Plains, again, trying to tease apart where does it work well and where are we having problems with it. In the longer term, later this year, we'll be trying to move it from just one forecast per county down to a 10 to 20 kilometer scale forecast, so that ranchers at opposite ends of the county might have different forecasts, and I think they'd appreciate that. I didn't show it on the maps today. We have been actually producing GrassCast maps for the southern plain states, Kansas, Oklahoma, and Texas, but we haven't done any validation there yet. And so we're not sharing those forecasts with the public yet. We've got a lot of work still, a lot of homework to do to make sure that it's actually working down there. We have a partnership in place over the next year to try and expand this to the Southwest and see if those 3 pieces, if the statistical relationships still hold up or not for that region. And then we even have some friends up in Prairie Canada, Alberta and Saskatchewan, who think that there's some potential to take this idea and move it to our rangelands to the north. So lots of potential. We're really excited, and lots of cool partnerships to help carry out this future research. So with that, I'm going to stop and open it up to questions. My hope is that we've addressed this first problem of translating a forecast into something more useful for agriculture. I'm not sure if I've accomplished this other one. Maybe you guys still feel like I just presented you with a map of scattered arrows. So I'll leave that for you guys to tell me how well we've made this understandable. And I'll turn it over to Rachel to manage questions.
Yeah, thanks, Dannele. That was great. I muted everyone as you came on, so if you have a question for Dannele, Feel free to hit the unmute button along the toolbar, far left, looks like a microphone, or put your question in the chat box.
Hi, Dannele. This is Holly. I have a science question for you. Why only 10 runs of the model?
Good question, Holly. It's 10 runs of the model in part because back in that step when we simulate the ET for 1986 to 2016, we chose those months or those years, quite honestly, because we know that if we went any further back in history, if we simulated 40 years or 50 years, that we would risk having the influences of long-term climate change entering into our data. So we're trying to simulate into the future. We want those future years to reflect kind of the climate conditions we're currently facing. And we think that the past 30 years is kind of the safest subset of data to draw from. Now, how do we get from 30 to 10? Again, we get a forecast from CPC that says it's going to be above average. Well, then we go to the top third of our historical data set and say, well, these were the top 1/3 wettest years that we've seen in recent history. Let's use the weather from them to represent what might happen this year.
Okay, thank you. I was thinking there would be more variability included in there, and so then I would think more runs, but you're just doing it for those 10 years. I understand now. Thank you.
Yep, and Holly, I think it's the difference between, I don't know how familiar you are with the simulation language, but we're taking what they call a bootstrapping approach, where you literally use data that you've observed, as opposed to a Monte Carlo simulation approach, where you would actually use those 30 years to create distributions and then draw as many times as you want from the distributions, and then you would get more variability. So that's an idea for the future for sure.
Thank you.
Hey, Dannele, it's David Brown in Oklahoma. Thanks for this. Really appreciate the kind of very deliberate pacing for all the details. I really understand it much better as a result of this, so thanks for that. I guess, if I have a concern, it's in the CPC information part of the tool, and I think you alluded to that at the end. And probably there are a couple of issues. I think there's a technical issue potentially with the way you are associating the CPC above average probabilities with your top tercile, because actually above average doesn't necessarily mean greater than 50% probability of above average. But I understand you guys you're having a chat with CPC about this, so that probably will get smoothed out, which would be good. I guess the more conceptual, and it's not a concern so much as sort of the standing challenge we all have about applying seasonal forecast information for any kind of climate services application, including agriculture. The CPC probability performance is just not very good in the spring. The skill of the forecast is poor and has been for probably 2 decades, probably even longer now. So sort of how do you overcome that in the long term? And then kind of a related question, is there an opportunity to incorporate some of the weather forecast model information instead, or as a complementary source of forecast skill? Because actually, even out to 15 days in some instances, you can get pretty good weather model, numerical model output. And I would have more confidence in that, frankly. Anyway, just some initial thoughts I had. This is a long conversation of many permutations, but some things to think about on the CPC piece. I don't know if you want to react to any of that.
Well, Dave, you're right on track. You've hit exactly on our current concerns and some ideas for moving forward. So high five to you for understanding it well enough to pick up on our major concerns and some potential ways forward. We will be meeting with CPC later this spring to talk about some of these issues. And I do really like the idea of trying to make better use of the 8 to 14 day outlook, because we do know that the skill of that is much higher. And so that's certainly on our laundry list of things to think about. Can we take that 8 to 14 day forecast and plug it into our day-cent model, and then use the CPC seasonal for the remaining part of the season that we, So great idea. It's on my list, definitely, of things to talk about with CPC and our GrassCast team. So thanks for those.
We had a couple more questions come in. I unfortunately have a hard stop in 4 minutes, so I'll tell you both questions, Dannele, and then if other folks have questions, you can see Dannele's email address on the screen, so please send her your questions. So we had a question asking, how do you account for antecedent conditions prior to spring, i.e. wet fall, winter versus dry fall and winter? And then the second question, how can soil moisture and snowpack data be incorporated where these data are available?
Great. So let me tackle the first one about antecedent conditions. It's a great question. And our ranchers give us this question all the time, again, because they're out there every day watching, what happened to the fall soil moisture, how much moisture is stored in that profile, and how much snowpack did we get to help protect that moisture. And so in the day-cent model, when we go to run the simulations of ET, we actually do what they call a spin-up period. And that spin-up period reaches all the way back into the 1890s for most sites. And so we've downloaded that historical data and fed that 100+ years of weather information into day-cent. And so day-cent is using that weather data to keep track of what was the soil moisture last fall, 2 falls ago, 27 falls ago. The snowpack I'm not so sure of. I know day-cent is capable of keeping track of snowpack, but I'd have to go back to the team and ask for sure. But I don't think we have the historical weather data to inform that piece of day-cent. And so we're definitely open to talking again with our NDMC and HPRCC partners. If we can track down some more of those historical pieces of information, day-cent is capable of keeping track of them. And maybe that answered the soil moisture and snowpack condition question at the same time.
Yeah, I'm going to have to close it because I'm going to use the same Zoom here. So thank you so much, Dannele. Thank you, everybody, for your engagement and questions. We'll be sending around a link to this recording, as well as if you'd like a copy of the PowerPoint, do let me know. It's kind of a big file, so I won't send it around unless you really want it. And I hope you have a good rest of your day, and thanks for joining. Bye, everyone.